And yeah, so let's first start by discussing some simple problems we had last time, right? Problems from last class. It's from last class. So I would rely on you guys to tell me the problems because I don't have them with me. So I explicitly gave some problems in the end last time. So if anyone can start with one of them, then we can discuss and then so on. Yeah, in that list. That's right. Yeah. So what was the question? Ah, yes, right. Reasoning that 1 plus 2 plus 3 plus till n actually gives us n into n plus 1 by 2. Yes. Yeah, summation. Yes, summation. So what I meant to ask is, as I said last time, you have to come up with a question, right, whose answer is the right hand side or left hand side, but naturally it will be right hand side first, maybe, whatever. But if you do the problem in a different way, then the answer would be the left hand side, right? So this is a very, and this is something that you cannot learn over a day. You have to, this will come slowly. This is the art. I mean, if you give me a hard question of this kind, maybe I cannot do. I have to think, and maybe then also I cannot do. So this just, these kind of questions can get very hard or very easy. This is a very easy version, but yeah. So come up with a problem. Yeah, whose solution, whose solution, let's say, whose answer, let's say, whose answer is RHS, and when done in a different way, like maybe using more casework or something, when done in an alternate way, answer is left hand side. So since then it will show that they're equal, right? Because they're the solution to the same question. Obviously there are very natural questions whose answers is the right hand side. So you can just do this problem in any way. But I asked it because someone had actually proved this in the class unknowingly last time. Okay, I'll also say that, but right now just think of a question you guys have already thought. Just think of a problem whose solution is the right hand side. Yeah. So don't worry too much about the logic of this statement, but just try to think of a problem whose solution is the right hand side. This is simply n plus 1 choose 2. We know that. So there will be many problems, right? Just use the definition of n plus 1 choose 2. Choosing two people from this and then yeah, simple. Yeah, that's right. So RHS is basically, you can just say this, right? RHS is basically number of ways. This is just standing for number of ways, just writing it like this. Okay. Number of ways of choosing two, I'll just say numbers here, two numbers from yeah, let me just keep it pens, because you see this decoration of pens or maybe something else, seating, these things can actually help you in thinking about an alternate way. If I just say numbers, then maybe it's just dry and it does not work. Yeah. I mean, it's not just dry for you. Even for hard problems, we have to decorate the set so that it's not dry. It's good enough for us to think at different levels. It just happens. Choosing two, you can say pens if it helps you, or you can think of something else if it makes you think, helps you get the answer. But this is certainly true, right? If you're choosing two pens from n plus 1 pens, so maybe I can just say pen 1, pen 2, pen 3. I'll just write n plus 1 pens. But now how can you do the problem in a different way? Now just think, I mean, if you didn't have the formula for n plus 1 choose 2, how would you do the problem? Just think ask yourself, okay, let's say I do not know the answer. Let's say I did not know the n plus 1. Let's say I was in class 6 and someone asked me to find the answer to this. How many ways can you collect 2 pens? So now do it in a different way, or rather I should just say in a simpler way without using n plus 1 choose 2. Different way. So we just need to do it in a simpler way actually. Like maybe making casework. All the choosing in which I am taking the pen 1 and all the choosings in which I am taking pen 2. Something like that you can try. Yes, exactly. That's how you will do it, right? If you didn't know the formula, let's say, right? So just take case 1, taking pen 1, let's just say pen 1 chosen. That's better maybe. Pen 1 chosen. Well, if you are choosing pen 1, then how many ways are there for the other pen? N ways, right? Now you take case 2, P2 chosen. Now this will not be N, right? Because N minus 1, yeah, right. Because, well, in some sense, P2 chosen should be N, but we don't want to we don't want to count the same thing again, right? Where P1 and P2 was chosen. So it becomes N minus 1 ways. And then you can understand, right? It will just keep going. N minus 1. And you have to add these, right? Because it's a case, it's a disjoint cases. I mean, right? These are solutions by themselves, right? So you have to just add it, and this is what you will get. I mean, you'll get it in the opposite way, n minus 1, but that's the same thing, right? So you see, it's just simple, right? It is just that you have to know what I was asking. Maybe that was not very clear, right? But this is your first. This is the first problem of this kind. There are many others which you can try, but this is the first one. Okay. So along these lines, let me just give you another question. So again, think about this. We will not do this now, but this is again very standard and very simple. Just try it. So let's see. So remove this. Yeah. So just a different problem, and do try this because now you know how to get started. So problem is same kind. Here, this is a very simple one. Okay, that is n choose 0. Okay, can write it in both ways. N choose 0, n choose 1, n choose n is 2 to the power n. You may have already seen this. Okay, so you can just but do write a proof. Combinatorial reasoning. Some of you may have done this in other places, but use the combinatorial reasoning. And here is a challenge question. Do try this also. Same flavor. No, this looks very same, but it's slightly more difficult. So it's a square. Okay, I just made it square. Some of you may also know the formula, but I'm writing it. That is not the point. To prove this combinatorially is a challenge. Again, think of a, wait, is this correct? No, it should be 6 in the denominator. Just check it for small numbers. Let's check it. for n equal to 1, it works. For n equal to 2, it's 5, and this is yeah, that's right, because long time I've not done this. So yeah, it's correct. So now try these two things. Okay, this one is going to be simple, this simple reasoning and casework, and this one is going to be a little more challenging. Yeah, but just note them down and try them. Yeah. So no, but by combinatorial reasoning, I mean that we are viewing the numbers on the right hand. We are viewing the numbers in this equation as the answers to some counting questions. Right, that is a perspective. To put it in another way, we are viewing one side as the solution of some combinatorics problem. That's the perspective from which we are looking at n times n plus 1 by 2. Right. So that is what I mean by combinatorial reasoning. But yes, usually it will involve like this. Flavor will be like this, that one side will be very easily interpretable, but the other side you have to do it by casework. Okay, but basically the meaning of combinatorial reasoning is that you have to come up with a problem such that when you do it in two different ways, you get left hand side and the other way will give the right hand side. So is it clear that then these two things will be equal, right? Because they're solving the same problem, right? Is that right? Yeah. Like why this will be equal? Because they answer the same question. No. It will continue, right? N minus 1, then you'll have n minus 2. Is that right? This is what we are getting here. And in that way, you will get this. That's right. So you see, this is really a new thing in the sense that, in what sense it is new? In the sense that these proofs are mathematically acceptable because they are very evident, right? Because we are obviously solving the same question in two different ways. Okay, but they're slightly non-rigorous. Maybe this is not the right stage to try to understand that, but if you just think about it, it is not a very rigorous proof in some sense, right? Or basically, it's like we are allowing some new senses to solve the problem. Is that right? We are. Yes, yeah. It's not very rigorous, but yeah, and the obvious, and also it's like we are using a new kind of sense. We are using a different sense of ours, like we are using a real life sense. So it really gives a different. It's like a completely different tool. Okay, so that's why it's very, that's why some problems which can be done by combinatorially and there is no proof of them mathematically, in a sense that using induction. These are not examples. These all can be done by induction, but there are yeah, for example, this one is a little tricky to do by induction if you try. But by combinatorial reasoning, it becomes just one click. I mean, of course, if you get the trick, otherwise you can't get started. It's a bit like that. Yeah, but it's a new sense. It's a new perspective completely. Okay. So please try this. And so yeah, so now we'll move to the next question. And it's very creative. It's interesting. I like it. Yeah. Okay. So you've noted it down. What was the next question? Anyone remembers? Hmm. Oh, wait, how many times? 5 times. Okay. Is an integer. Okay. And look, one second before we do this, I forgot to mention that how how I forgot to mention what I meant by someone already proved this last time. Okay, so if you remember last time we kind of had okay, even I don't remember the exact thing, but it was kind of like there were n+1 seats, right? And we had to place um, a man and a woman such that someone sits before and so on, right? We had to place one man and one woman such that, let's say, the man sits before, or whatever, let's say the man sits before, right? And so this one was obviously, so one way we did this was n+1 choose two, just choose two places, right? But then I remember someone else saying that case one, put the man in the first place, right? Same problem, put the man in the first place, m1 in first seat. This case. Now, in this case, when you put the man in the first place, then for the woman, there are n choices. So then this gives you n ways. And similarly, someone said that put the man in the second place. Then the woman has n-1 choices, right? And this is a completely different decoration, and it kind of makes it more obvious, right? I think Ishana was saying this. Yeah. Right. Yes. Yeah. That you put the man in the second place. Now, obviously, it's very obvious the woman cannot go in the first place. And so there are n-1 places and so on. So there are n+1 and so n places. You can understand. You see, I think this is where I picked the motivation from, to give this problem, because already you had yourself, someone that said it. So right time to start exploiting that technique in other places. Okay. Okay. Okay, now let us come to this question. Yeah, and this also I gave for a certain reason, but yeah, let's try this first independently. So this is an integer. Again, the intention of mine to give this question the way was that try to do this combinatorially. Again, using combinatorics in, if you can say, number theory. So again, what do I mean by do this combinatorially? Show combinatorially. I mean that think of a problem, think of a counting problem whose solution is this number. Then the number has to be an integer, right? There is no other way. Right. Okay. So you agree that if you can think of one, just logically speaking, let's get the logic out of the way first, right? If you can think of a counting problem whose answer is that thing, this big number, then we have nothing to do. Then we are done, because it has to be an integer. Now the challenge is to think of a counting problem. But this is not the only way. You can also try to use, which is semi-combinatorial, I can say. You can also try to use the chooses, that this is something choose something, time something choose something, time something choose something. Just like the last class, we had something like let's say 20 choose 2, remember, 18 choose 2, then 16 choose 2. And if you actually break this down, this turns out to be 20 factors. It's just a manipulation. Use some manipulation and write this as a product of chooses. right? Choosing something, and then you can also get your problem after you make the manipulation. You see, if we do this, you see this comes out to be like this 10 times. So this is of a similar nature, less homogeneous, but similar. Yes, that's right. But let's continue with that approach, right? So if you're saying you write it 65 factorial, see, there is actually no other option, right? You have to write 65 factorial here if you want to create a choose. So you multiply, divide by that. So at least we can get started and see. So yeah, let's see what we. Yes, that's the good first step. So what's next? Let's think. This is obviously just 100 choose 2, 102 choose 65 or 37. You can say anything. So now at least the task is smaller. Right? Now we just need to show that this is an integer. And you can see the pattern. What we can just continue the pattern. Think. Yeah, right. That is what it is. That's right. That's all we have to do, right? So we have the 65 factorial, and then you have 13 factorial. So what should be this thing? If you want to make a choose, just 65 minus 13, right? Just to create the choose. So that's 50, 52. Yeah. Yes, and then you know how to continue. Yeah, something. 13 factorial, 13 factorial, 13 factorial. Yeah. And you can just continue like this. And you basically end up writing this as a product of chooses. Okay. Yeah. So this is a rather simple problem. So we actually did not directly come up with a counting question. We did not directly come up with a counting question, but if you do these calculations, this is not the best solution in that sense. In that sense, but it's a absolutely correct solution. Let's first write it down and see what we got. So we got something like, yeah, so let me just do one small thing. Let me write it like this only. 37, 65 choose 13, 65 choose 13, 65 choose 13. And I think one more. So it's not 65. It's not, they are not 65. That reduces. Yeah. 13 and this would be 52. From here, now you can think of a counting question. At least from here, we can obviously think of some counting question. $26. Now you can think of some counting question. Let's try to do that. Okay. So the problem is solved. There is no issue. Solution. But yeah. So now that it is more direct, think of a counting problem that has the solution. Okay. Please try this. We will also actually visit such counting problems. Just that was the next thing I had in mind. Just a continuation of the kind of things you got. Okay. But I wanted to first revisit lattice path things. But anyways, is this approach clear? This cancellation and so on. This writing it in terms of chooses one step at a time. Is this technique good? Okay. So let me also then just give a extension of this problem that you can try. So first try to do this. This is just straightforward. You can just do the same manipulation. Okay. You can do the same manipulation. Yes. Yeah, any question? Yes. Yes, right? It's surely an integer, right? Because it's a product of integers. But the only difference is that this is not completely combinatorial, right? We did some manipulations. Is that right? Yeah, we did. Yeah, it is. Yeah. 13, and then one family you will need 37 people. Yeah, so you see, yeah, you can see it, right? Exactly. So when you do the next problem, we'll do the next problem, this will be just you connected. So that's a very good point. It is just like the man-woman problem. So it's just like there are 102 people in total, 37 families, sorry, one family with 37 members, or one group with 37 members, another group with 13 members, another group with 13 members, and so on. And maybe they want to, each group in its own wants to sit in its ascending order of heights, not together necessarily, but ascending order of height as we move from left to right. But this will be clear when we do the next question. So yes, so that will be a direct thing. You don't have to do these cancellations. See, you may think, okay, why am I stressing so much? What's wrong with doing this multiplication division? There's nothing wrong with that. This is completely good. But then we are sort of not seeing this directly as counting something, right? We are seeing this through the lens of algebra, through the, not just algebra, actually we're using rational number property, right? We're able to divide by 65 factorial. right? So because you're using more tools, you're sort of restricting yourself. Okay, now you will not, maybe you don't see that why you're restricting, what's the restriction, but the point is that if this thing is true here, it may be true in some other way. Like this may be a polynomial in 102 factorial, something like that. Okay, like it can be some more general. Maybe this 102 can be replaced by let's say 1 plus x squared to 1 to x to the power 102. Some other thing which is not 102, but it is a generalization of 102. This is like a generalization of the number 102, because when you put x equal to 1, you get 102. But then it's more. It's in a bigger thing, right? If you see like that, then if you write this also in that way, then to prove it, maybe you cannot multiply divide. There may be some objects in mathematics which numbers you can multiply divide, maybe polynomials also you can multiply divide, but there are other things which you cannot multiply divide. And there, if you have this other way to prove thing by viewing it in a different way without multiplying dividing, then the same idea will work in that place, right? So the lesser things you can use, in the sense that the lesser, you know, cutting pasting you can do and still do your proof, it means that it will pay off later on when you try to prove it, see it in a more general thing. Yeah, but as of now, and it's also more, I mean, you can feel it, right? You can directly see it as a counting problem. It's direct. It's like you just see it directly. Yeah. Okay. So then it's fine now. So this is one question that you can try, but this is a straightforward thing. Let me also give a slightly challenging thing. So just in the same question, let me make a variation, and you will also see some curious thing there, hopefully. Obviously, here also you see that these things add up to 102, right? 37, 13, 13, 13, 13, 13. They all add up to 102. So here also I'm keeping this thing the same. And then, okay, I try to show that this is also an integer. So further dividing by 5 factorial, but this is also an integer. So this is definitely a generalization, right? In some way. Try to do these things. These two, okay? Just give them a try. Okay, so note them down. Let's go to the next problem. So any questions with the problem I've given or explanation? Okay, so then let's go. What was the next question? Let's first clearly state it. Mm-hmm. Mm-hmm. That's yeah, that's not need. That's right. Yeah. Yeah. So for any family, the members are in ascending right, ascending order of height from left to right. Just to give a example, so yeah, so suppose there is family 1. I will not write everything, but this may still be helpful. There is family 2, I'm calling with B, and let's say that the heights are like this. Okay, just like what cases? What cases? No, but if we finally didn't solve the problem like that, right? We solved it by choosing places and so on. Remember? That was a real, because again, casework will again, this here casework will just get out of hand completely. Yeah. You have to do, let me just give an example. So there, whatever, some number. Hmm? Yes, it's completely like that problem, right? In fact, in this problem, if you four families, if you make four families, but they have 0 members and they have 2 members each, then it becomes kind of, yeah, or more family. But yeah, so this is a generalization, meaning that you can put some special values in this, you can get that problem. Right. So for example, it could be like this: A1 can sit here, A2, A3. So they have to. So if they only care about themselves, then A2 should also be to the right, and A3 should also be to the right of A2. Okay, A2 should be to the right of A1, and A3 should be to the right of A2, like this. And then similarly, you could have like B1, and then the B2 may actually sit far away, and then B3 may be like this. But finally, the relative order. So the word is relative order. Like relatively, if they just care about them, the BIs, they will see each other sitting from left, arranged from left to right in terms of height. Okay, so it's not like the whole, if all of them stand up, then it will be an ascending thing. No, right? But if all the A's stand up only, then it will be an ascending thing. If only the B's stand up, then that will be an ascending thing, and so on. Okay, all right. So please say if the question is not clear. Otherwise, let's try to solve this. Okay. Good. So since you guys see the similarity of this with that, try to also see the similarity in this in the way you approach. Right? We had chosen first in that problem, we chose, let's say if there were 10 men, 10 women, we chose 10 seats for the women first, or for the men first, right? So something like that maybe, or or right, you choose 2 seats for every pair. Sorry, that's not what we did, right? We choose 2 seats for every pair. So exactly right. For every couple, so for this couple, we chose 2 seats. Absolutely right. We just choose 3 seats, and that's it. Absolutely, just 18 choose, because once you choose three, so the thing is that, again, I'm not writing this, but once you choose 3 seats, you just cannot do anything more. You have to just place the members in the leftmost seat you chose. You have to place A1, the right, and then so on, right? And then just continues, right? For the second family, 15 choose 4, right? But make sure you understand this. When you choose 4 seats, then that's all, right? You cannot do any permutation because of the order, right? You have to just choose 4 seats for B4. right? Choosing 4 seats. And after that, any permutation? No, only choosing 4 seats. Once you choose 4 seats, because of the order, they have to be placed in a particular way. Okay, so I'm not writing it. You guys can complete it. Okay. Okay, now I think we've spent a lot of time on these questions. So now we just try to do this extension on your own. In the sense that I mean that try to connect this problem with the last problem I asked, combinatorial reasoning. Okay, think of a combinatorial problem. Now you can think. So take a minute and see if this reasoning is clear. I'm not saying too much now because I think if you think on your own, you can get it easily. Hmm. Hmm. Yes. No, not double the number. Yeah, that's right. So if it was right, so then that would basically mean ascending or descending, right? That's the same thing. Yeah. So in this case, basically after choosing, there are two ways. So let's just show it once. So let's write it. So 18 choose 3 ways to choose 3 seats for family 1. So let's say you chose this seat for family 1 and this seat for family 1 and this seat for family 1. Now you're allowed to go ascending or descending. So you can start with the shortest member and do this, or the reverse as. So now it will be 18 choose 3 ways to choose, but then to multiply by 2 to permute. But this is not full, it's not all the 6 permutations. No, this is just 2. So then it will become 2 to the power and so on. Right. Then it will become 2 to the power 4 times the answer. Right? 2 into 2 every time. Yeah. So these are subtle variations, and more variations you will see will keep coming. Yes. Okay. Let me just give a problem of the same type. Okay. This is not hard or easy, but it's similar question. And let's see if we can do this. But maybe that's a more abstract. So we have 2 sequences. We have 2. We have 2 sequences. So one is the sequence A1, 2 increasing sequences, A4, and we have B1, B2, B3, and B4. Okay. So how many ways to merge the 2 sequences? So again, by merge, I just mean that, you combine these 2 sequences to make a sequence of size 8, but the relative order should not change. Right? So I'll just say this. Now you just try to format it. Okay. Hmm. No, you don't have to place A1 between them, right? All we need to care about is that if some term is coming before some term, then in the big sequence of size 8 also it should come before, somewhere before. Yeah, something like, yeah, exactly. That's okay. So then it's very trivial. Yeah, that's right. That's right. That's exactly what it will be. Yes, that was very trivial. Okay, so what to do? So let's then ask a harder question. But still, please write this. Okay, please write this. All of you should write this still. A different one, maybe. Yeah, let's just do this classical one, right? How many permutations? And we want to do this by the same technique, just to see the power of it. How many permutations of, you can just take some word which has a lot of repetitions. Okay, so for example, you can take this oligopoly or some other word, right? How many permutations on this word? Don't use any known formula. Try to do this from the ground up, from first principles, and you can see if this technique that we have seen, can be useful or not. Yes, can you give a more explanation? It is correct, but can you give more explanation? If they come first, what do you mean by if they come first? You mean like this? But this is just one way. That's right. And we chose. Mhm. Okay, so they enter first, right? And so I will not say nine choose three ways to permute them, but I'll say nine choose three ways to choose three places for them. Right. Choose places for the O's. And once again, so it's in some sense it is slightly different from the families question because it's not like there is no order, but in some sense it is the same because once you choose the three places, then there is nothing more to do because they are all O's. And now you can continue the problem. Okay, I'm just leaving it here. Okay, you can just see how to continue. Think about this, you see, and this some of you may recognize is a type of permutation question, right? Permutations with repetitions. But now you see the type that we are doing this is just by counting, that's also counting by choosing places. Okay. Okay. So this is also simple. Please complete these things though, okay, and check your reasoning and so on. This is not the best way to do this problem from one perspective. This is not a good way to do because it's hard to generalize this to things. But this method here actually fits very well. Just does it means it's very rigorous proof that we are giving, right? That formula is a little hard to prove if you try to do it in a different way. Okay, so then let's come to more variations. Yeah, this is something that we have already done, but let's just do it again. Let's say that there are 9 balls and 3 boxes. Okay, box 1, box 2, and box 3. Yeah, so let's keep this simple for now. So box 9 distinct balls, obviously distinct balls. So box 1 can take 2 balls, and box 2 can take 3 balls, and box 3 can take 4 balls. How many ways to distribute? No, they're distinct. Distinct. Identical also we'll do, but not now. That's more difficult, I think. Yes, but again, give an explanation. Yeah, you're right. The answer will be the same, and even the way similar. But let's say the boxes are like families. Absolutely, that's it. Yeah. So box 1 is, and so balls are like the places. Okay, balls are like. This is not the only way to do this. There are more straightforward ways, if I may say. But this is a very nice connection. Balls are like the places. Okay? And the balls are the places. So there are like 9 places. I said it is strange to think the balls are places, but balls are places here. Ball 1, this is just to see the connection. Ball 3 and so on till ball 9. Now you have to just choose 2 places. That would mean those 2 balls are going to go in box 1, or that's the same as choose 2 places for box 1, choose 2 places for family 1. Same question, same answer. Right? Now you see the connection. But the direct way one can say is that for box 1 you choose 2 balls. Just choose 2 balls for box 1. That's 9. Choose 2. Then choose 2 balls for box 2. That will be 7 from the remaining, right? 7 choose 3, and then that's it. The rest is 4 choose 4. So you have to just put them in the another way, but same answer. Okay. Okay. So just take a minute and see if this is okay. Okay. Yeah. So there are so many ways to approach this, and you see they all kind of the same answer. Now, let me make this problem slightly more interesting, and this will connect with the other things that I've given and some problems I've given. And that's all I'll say. So let's just clear this. Yeah. Let's say that now we have, let's increase the number of balls. Let's say we have 15 balls, 15 balls, and we have, let's say, 5 boxes. Okay. And box 1, I should say, can take 3 balls. Box 2 can take 3 balls. Now, so let me just say this clearly. 5 distinct balls five identical boxes, 5 identical boxes. So now I cannot say box 1, box 2, and so on. I will just say 3 of the boxes can take 3 balls each. No, that will not work. Can take 4 of the boxes can no. 3 of the boxes can take 4 balls each. A minute. Oh, this will, yeah, that's fine. Yeah, and the remaining 2 boxes, yeah, and the remaining and 2 other, I should just say, not remaining, right? And 2 other can take 2 and 1 each. So that just to make sure that total it is 15. How many ways to distribute? Like ball 1, ball 2, so on. 15 balls. But these are 5 identical boxes. Yeah, so in some sense that logic is correct, right? Because if there is a ball, so if there is a box that takes 4 items, 4, and if there's another box that takes 2 items, these, even though the boxes are identical, now they are kind of different. Uh-huh. 3 O's. Hmm. No. So you see the words. So in the words, the letters were what? The letters were no. The letters are boxes. No, the letters were not. The letters were. Okay, let me this thing. That's right. And the letters were the boxes. Yeah, I mean every letter of one type was one type of box, right? Yeah, like the O's were boxes of one type, and the E's were boxes of another type. But there, the boxes were kind of distinct, right? There, the boxes were distinct. Yeah, that's the difference between that, right? The O's and L's are different boxes. But this problem is slightly different from that. You'll see the answer will also have a slightly different flavor. Yeah, but this so but what you said here is that we can take these three to be identical. So this will take 4, 4, and 4, and then these two to be kind of distinct. I mean, distinct from these and also distinct because this will take 2 and 1. Just looking at the capacities. Yeah, because the one that take 4 boxes and the one that take 2 boxes, they're now getting distinct. And because you cannot really permute and so on, because it will change. Take your time, think about this. We'll just wait. It's a new question. Need some time to think. Hmm. Fifteen choose 12. Okay. Okay, let's see. So you're doing 15 choose 12. Okay, that's interesting. So you're choosing the 12 box, 12, choosing the 12 balls, choosing 12 balls for the first 3 box, for the 3 boxes, for 3 boxes. And then use what's the next thing? Oh, you didn't say 15 choose 12? Sorry. Mm-hmm. But remember, we don't need to arrange the 12 box. We just need to distribute the 12 balls. Yeah. Yeah. Decide which one to give to which one. But the problem is that they are all identical. Okay. That is the slight problem. I mean, so if they were all distinct, then you could have done this problem by saying, I'll choose this. And then from these 12, I will choose 4 for the first box. And then I will choose, this will be 8. Then I will choose 4 more for the second box, and the remaining I'll give to the third box. Right? And then fourth and fifth box we can deal separately. You could have said this, but this will not. So why will this not work in this case? After choosing 15, after choosing 12 from 15, then giving 4 to the one, 4 to the other. This will not work because, I mean, look, in this one, it's like suppose here in 15 choose 12, suppose here you chose 1 to 12 balls, the first 12 balls. And then in this, you decided to give like this, right? And to this one, in this one, you means the second box, you gave 6, 7, 8. And then the third box, you gave the remaining 9, 10, 11, 12. You did this. But the problem is that this one way, right? The other way, So the other way would be that in this, you choose, means for the first box, you give 9, 10, 11, 12, right? And to this, let's say you give this only 5, 6, 7, 8. And to this, in this one, you choose obviously 1, 2, 3, 4. Is that right? These are two different ways to distribute, isn't it? At least if the boxes were distinct, then there are two different ways to distribute. And in this way of counting, they are different, right? First choosing 1 to 12, then, so if you look at below, if you look at the below one, first we choose 1 to 12, then you choose from 1 to 4 out of them and give to the first box, and then 5 to 8 you give to the second box, and 9 to 12 you give to the third box. And the other ways to do this are different. But it's not different in our case, right? Because it's just the same partition, right? It's the same because the boxes are same. Right? These two are actually same for us. That is the problem. Because if you do this, 5, 6, 8, 9, 10, 11, 12. If I do this, now if I shuffle any one of them, right, I get this other one. If I shuffle, if I place this here and place this here, but that's not considered to be different because the three boxes are the same, right? So it is the same distribution. The boxes are same. I mean, the information is same that, one box got 1 to 4, the other box got 5 to 8, and there was one box which got the remaining. That information is the same, right? And that's all we care about. So how do we adjust this answer? That's also wrong. That's undercounting, right? This is overcounting, but 15 choose 12 will not work because 15 choose 12 does not take into account, if you only take 15 choose 12, then that forgets the fact that there are three boxes at all, because three boxes at least create some distinction, right? Like this at least says that 4 and 5 are in different boxes. That we are not capturing in 15 choose 12. So the answer is somewhere in the middle. So the answer is to basically you to consider them to be distinct. So first step is that you imagine that they were distinct and you do your counting, which you can do by 15 choose 12, or you can directly do the other way is to the same answer you will get, but I mean, you can just directly do 15 choose 4, and then you can do 11 choose 4, the same thing, and you can do 7 choose 4, right? And then there are 3 left that we'll think later. So you do this, but then you see when you do this, right, then you get a lot of arrangements, right? But the point is that if you take any particular arrangement like this, right, there are six permutations of this. So if you take a particular distribution, there are 6 permutations of this distribution, but all those 6 are considered the same when the boxes are identical. Right? Doesn't matter, right? So we can take the 6 permutation of these. So for example, we can take one permutation. So basically, I'm just shuffling the boxes. Yeah, I could just say that there are 3 factorial ways to shuffle the boxes, and they will give you 6 distributions, which are counted here, but they are same for us. So we have to divide by 6. Right? You can think of this in several different ways. So you can take this particular permutation. In this way, you can create six different permutations. These 6 things, though, are the same because they have the same information. There was some box which got 1, 2, 3, 4, some other box which got, okay, and third got the remaining. So, but these 6 we are counting as different because easier to do like that. But then we know we can divide by that, right? Because we have 6 permutations are becoming 6 different distributions are becoming 1. And that 6 is not a coincidence, obviously 3 factorial. We can see, we already see that 3 boxes. And that's it. And the remaining we can just continue the usual way. 3 choose 2, and 1 choose 1. Here we don't have to divide because these are already different, right? These are already different because if this has 13 and 14 and this has 15, then I mean, I cannot shuffle this, right? Because this needs 2 box. This needs 2 balls. I cannot shuffle this. So I'm not over counting if I just multiply, because I cannot identify 2 different distributions. I cannot collapse 2 different distributions like I did here. 6 different became the same because I could permute because sizes were the same. So you see this, try to simplify this and see what you get. This is kind of interesting because it will give you 4 factorial cube, and then you'll give a 3 factorial here. And okay, so you can see we already saw something similar like this earlier in the class. So yeah, we'll leave it there. You have to think of it now. Okay. So now take some time, take your time and see if you have any questions related to what we did now. And yeah, then we will stop. So just, that's right. Why did we divide by 3 factorial? So see this that we are counting. Right? So let's forget about the other 2 boxes now. That doesn't matter. See, this is the number of distributions if the boxes are identical. So if the boxes are distinct, right? If the boxes are distinct, right? Then we have this many ways. Yeah, you agree with this? Now, if what happens when the boxes become distinct, but the boxes are distinct, right? The boxes we have are distinct. So what does that, how does that affect the counting? Think. How can we relate to these 2 things? So we need to see if the boxes are distinct, then obviously there are more different countings, right? If the boxes were distinct, then these 2 are different, right? This distribution and this distribution are different. What have I done? I've taken this distribution D1 and I've just shuffled and I've got a distribution D2, right? In this way, I can do 3 factorial distributions, 3 factorial shufflings. And I can get 6 different distributions in the distinct case, if I consider them distinct. But in the identical case, so I've written things wrong again, boxes are identical. Right? So initially, the boxes are identical, but to solve the problem, we are considering that the boxes are distinct. Okay? If the boxes are distinct, then there are this many ways in total. But if we pick one of those ways, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, if the boxes were distinct, then I have these distribution, but then I can shuffle and create 6 different distributions, right? But all these 6 distributions, right? But these 6 distributions, they are the same if the boxes are considered same, right? Just look at these 2 distributions. How are they different, right? They are the same distributions, right? So if we just write them here side by side, 5, 6, 7, 8, and then you take this. I'm just writing the same thing. Okay? This is one distribution, and this is another distribution of 1 to 12. These 2 are the same distributions. If the boxes are identical, then there's no way to say that this is different. This distribution is different from this. Right? There is no way to say that they're different. right? They are the same. So in this way, you see 6 different distributions become the same. So 6 distributions collapse to the same distribution. 6 different distributions in the distinct case become the same. And this way, every 6 becomes 1. And so if you divide by 6, and that 6 is coming from 3 factorial, right? Right. So this is a variant, right? And this is an interesting variation. And we will further do more variations later on when we put some cyclicity and some order inside the boxes and different ones. But we will only, so I'm not doing repetitions of the same. That you have to practice with different numbers, or I'm giving some problems, but also I've recommended some text, like Brualdi is one. Okay. But the other book, I think there is another book, Principles of Counting. So this is another book I thought now I can say, because now you guys have learned a little more. So, but you try to solve the problem I give, do that first. And if you get time, then maybe try Brualdi. And if you get more time, then try this. Principles of, I think it is counting. What was the name? It is, maybe some of you will know. It's Chuang or Chuang should be the pronunciation, I think. Something. So let me just see. Counting. So if I type counting in my thing, a lot of things come, so I cannot really. Anyways, leave it. No, I don't get it. But let me search on the internet, then I can show you. Counting. Yeah. Principles and principles and techniques in combinatorics. I thought it was only for counting. Yeah. So principles and techniques in combinatorics, not counting. Sorry. Principles and techniques in combinatorics. Please write this. And it is Chuan. Just this name will give you the book. Okay. This is the book. This has, at least I remember that the counting section was very nice. I have not seen that book in many years now. But yeah, if you check that out, you will see. So it has a lot of variations of these balls, boxes, things also. Okay. Obviously, there are other places, but they are more complicated. But in any case, first try the questions I've given, and then you can look at this book also. So what are other places you guys are solving counting questions from, if any? I also like a JE book and so on, which you can also look at. So anyone has lately solved any counting questions? Uh-huh. Okay, right. So, but you're getting more problems. Okay. So that's good. Okay. So is that any book or some homework sheet, something like that? Yes.